Okay, why don't we get this kicked off? I think we've got enough people still filtering in. Hopefully, they can find good seats. So, hi, I'm Wade, uh, responsible for technology here at Grand Rounds. Work with a lot of amazing people, a lot of them in this room. Hopefully, they have introduced themselves to you, but if not, anybody that's got on a Grand Rounds t-shirt or has one of these name tags that you can see there from Grand Rounds, please introduce yourself. They'd love to meet you, and they're really nice people to boot. And so with that, what is Grand Rounds? Like, I'm assuming a few people kind of want to know about that. I got to know Grand Rounds just recently, joined in January, and learned a lot as I was going through the interviewing process, and had Owen, the CEO, telling me a lot about Grand Rounds and the mission and things along those lines. And I have conveniently not said what Grand Rounds is yet, but I'm going to. The interesting part was fast forward to just a week ago, and it was one of those weeks where it was just this surreal set of things that all happened inside of a single week. I'm in an interview. We had somebody come in. We're interviewing. I walk in, pleasantry, pleasantry. Hey, how are you doing? So, what interests you in Grand Rounds? You saved my sister's life. Record scratch moment. It's just like, oh, I wasn't prepared for that as a statement. And then the exact same day, we had another employee that joined the company, of a couple of them, but went to introduce myself to this new employee. And it's like, so why'd you join Grand Rounds? You saved my life. And it's like, okay, this is a theme, and I'm not sure how to actually answer this moving forward. But the interesting part is, like, I'm sure that everyone here knows somebody who has had a medical condition and they felt like they weren't getting the right help. And it didn't help that they were kind of getting the runaround in certain cases, and you needed to make progress. And this is somebody's life that you were dealing with. And it's a big problem. If you look out there, there's a lot of different journals and magazines and professionals that say that somewhere between 45,000 people to over 400,000 people a year die in the United States alone based on being misdiagnosed or given the wrong treatment. That's pretty serious. And it costs a lot if you think about that. These little known facts that I just didn't know walking in: 1% of cases drive 49% of the cost. 10% of the cases drive 90% of the costs out there. It's the second most costly thing for companies outside of wages. And so if you think about that, you start to think about, like, what can we do to help solve that problem? And science can actually help a lot. What if you had access to all of the right information so that you could actually go through and find who are the best professionals to help out in what sorts of cases, and what's the right treatment path to help somebody get genuinely better, not just a little spot solution here. Well, it turns out you can use data science and professionals to figure out better pathing and come up with superior answers. And if you look at that, we have seen the people who have went through and used Grand Rounds to help find a better path. 67% of the people that use Grand Rounds actually have a different diagnosis or a significantly different treatment plan that they choose to adopt. That's cool. Like, that is genuinely just a cool statement to make there, full stop. The even cooler part is their employers saved thousands of dollars per case while their employees got better. That's what Grand Rounds does. And if you can do this consistently, you grow fast as a business. There's a lot of businesses out there that you look at, health tech, and they're not necessarily having that growth story that you want to see. Grand Rounds is very much going through that path because as employers find that they can save thousands of dollars per case and make their employees better, that's something that they want to do. And we've had a lot of success in market, and we're continuing to grow along those lines. Which brings us to tonight's subject, right? There's previously, before here, I was at Twitter. we understood big data. We would take massive amounts of data and try and answer directional questions with that data. Here, we've got a very different problem. We're trying to solve a deep data problem where we can actually take information, some of it very not precise, and be able to create clear, crisp decisions that actually drive treatment. And so we're going to talk a lot about data today and how we can actually use that to make better and better decisions and a lot of different aspects of that overall ecosystem. And we have got a lot of great speakers lined up to be able to do that. So I would be remiss if I didn't stand up and say we are hiring. And so if anybody is looking for that next stage of their career, we have almost every opportunity for you, from managers to senior ICs to working on the application side of things to working on the data side of things. If you're interested, go to our website. There's a careers section. All of them are listed there. All right, so without further ado, let's actually get on with this. I'm going to invite up Jay Odita.
Hi, everybody. First of all, thank you all for coming. I love these events. It seems to be growing every single time we do them, and I seem to be meeting more and more exciting people every single time we do these. So thank you all for coming. My name is Jay Odita. I lead data science here at Grand Rounds, and I decided that there is no better way to introduce myself than sharing really embarrassing childhood photos of myself. So as a kid, I kind of found that my interests fell into two different buckets. One was interests in the arts. I sang, I danced, I painted. Here I appear to be coloring on a newspaper for some reason. And math and science. Here I'm trying to understand the effect of salt on the freezing temperature of ice. But growing up and kind of the way that the education system is set up here in the United States, these worlds are painted in a very distinct and separate way. So in art class, you can kind of do whatever you feel like. And in math and science, there was always a right answer, and you got it wrong if you did not have that exact answer. It didn't help that they would always draw this picture, kind of defining a left brain person and a right brain person, and you take these quizoids that would kind of tell you whether you're a left brain person or a right brain person. Again, all these things kind of reinforced that you had to be one or the other, or that these things are very different. And so time came when I graduated high school and I had to decide what I was going to do my career in. And it really felt like I had to make a choice between these two major areas. And so I put my practical hat on and said, okay, I'll go down the math and science route. And I started to go to school to gain the technical competencies that I thought that were required to be successful in a career. And I had chosen biology and bioengineering as my path. So I went to school and even more school, very typical path of a data scientist. And eventually said, okay, maybe I have learned enough to actually put this into practice and make a difference and do something with all these skills. And I was very lucky to find Grand Rounds, where, as Wade mentioned, we're saving lives on a daily basis and really making an impact to the way healthcare happens in the United States. And I started to work as an IC here and make that impact. But what I found along the way is that when you move into research or R&D disciplines, there's no longer a right and wrong answer, right? It's not like your science teacher already knows the answer to the experiment and you have to find that exact answer and write it down on the test. Instead, it's completely open-ended. And while you need that technical base to do well, either in the academic world or in industry, the people who did the best and really succeeded, had the most publications, the most read publications, the most impact, were those that were really exercising that creative, insightful parts of their brains. And I find that on my team as well, right? Of course, you have to have the technical knowledge to do well, but the people who are building the best models that are enabling us to route our members to the best clinical care are those that are taking the data with all its issues and nuances and craziness and able to creatively make choices that will drive our models in the right direction. And data science is kind of on the worst end of this, is having like a really left brain reputation. And it doesn't help that the word machine is in machine learning. This is actually my son. He's my biggest assistant. I mean, the notion is that you're taking data and some logic, math happens, and you get your predictions. But in actuality, and particularly with the health data that we work with here at Grand Rounds, there has to be this other layer that comes in between. You have to understand when you're generating labels, what the impact of making your design choices in different ways is going to have, and have intuition on how that's going to impact your results. The data isn't just columns of numbers. You have to think about how it might link together longitudinally, what that might mean for a patient's actual story over time, their severity, their needs, and put it together in ways in which you're thinking about the bias in your underlying data. What are the issues with your data? How can that impact my results? And what can I do to minimize that bias in my results? And if you actually apply some of this intuitive, creative, insightful piece back into that machine, you're going to get much better predictions. So today I thought I would take you through an example of a project that we work on here at Grand Rounds. I'll start by explaining some of the issues that we have with our data that are really motivating us to apply that insight upon data, and then talk you through an example that I think my team really applied a very creative lens to. So here are two examples of the type of data we have at Grand Rounds. First, data that describes our providers. This could be their names, their addresses, their specialties, their phone numbers. Second, medical and pharmaceutical claims data. So this is every single billing interaction. You see patient X going to provider Y on some date, having done this because they have this problem and it costed this much money. But all of this data is incomplete, lots of holes, lots of errors, not up to date. And these are just a few of the problems that we start to see within this data. So the example that I'm going to show today is a model that we built to try to improve the quality of our specialty tagging around the providers in our system. And of course, I should not get credit for this work at all. I work with an amazing, amazing team of people, some of which are pictured here, who made huge contributions to this project. So as Wade mentioned, one of the biggest focuses of Grand Rounds, as well as the data science team, is to try to match our members with the most appropriate and highest quality medical providers for their needs at a given point in time. And this is where the data science team spends the most of our time. However, even if we're able to surface the world's best medical recommendations, and if you cannot actually make an appointment with that amazing recommendation, we've done nothing at all. And so here's another challenge that we face. We make these amazing recommendations. Our member is super excited about them, but then they get on the phone trying to make an appointment with this cardiologist. And if they find out that that person is not a cardiologist, they're going to instantly get frustrated and probably never come back to Grand Rounds. But this is a real problem. The data that we're using is stale and erroneous. I don't know if any of you have been on an insurance website and how many calls it has taken for you to actually get an appointment. Our underlying data is really no different from the data that is on that website. Subspecialization adds a whole other layer to this problem. There's a lot of overlap where one doctor might specialize versus another, and the definitions and the taxonomy are not consistent. Further, you can have multiple subspecialties. So despite this kind of mess in the underlying data, we still want to make sure that our member has an awesome experience, that once we're recommending the highest quality providers for their care, that they're actually able to make appointments with them and get to those providers. How do we achieve this? So step one in a machine learning problem is to come up with some known truths. This is what you're going to benchmark the rest of your model off of. So in this example, we might need to know for certain that some population of providers are truly cardiologists and some other population of providers are truly not cardiologists. Then, given that prior, we can find patterns within those two groups to understand what are the characteristics that define a cardiologist or in the characteristics that define a non-cardiologist to predict where we don't know the answers. Are you a cardiologist or are you not a cardiologist? So here are two different types of ways we can get that ground source of truth data. The first is human learning. So we described a product where on our app, we can surface recommendations for one of our members' needs. We have multiple other services here at Grand Rounds as well, and some of those are more high touch. And as a result, we have an amazing patient care team that's actually on the phone with both patients and providers all the time. And through their calls, particularly to provider offices, they actually get information around, hey, is this office a cardiologist's office or not? And they can take that information and surface it back to us for us to use in our models. So this data is great. It's up to date. Someone's actually telling you on the phone, this person is a cardiologist. It's a pretty high accuracy. Now, we don't know the conversation and we don't know the questions asked. So sometimes the data is difficult to interpret. And of course, this data is very sparse, but it is kind of the best that we can do right now. The second source is all of our commercial and public data sources. So these are national registries, fellowship data, certifications data, kind of big data sets that cover many, many more of the providers and describe what their specialty might be, but this data is often stale. For example, you might register with these public databases right out of med school before any specialization or before you've really chosen your true path. Further, there are other nuances where not all specialties even require a fellowship that add noise to our system. So we have these two options, and the next question is, how can we use this to try to understand provider specialties? So if all of these registries are very stale and old, maybe instead of using the stale data, the actual answer to the question is, well, can we figure out what the providers are actually doing in their day-to-day today, this week, this year, and use that information to predict specialty? So to understand what they're actually doing, our best data set is our medical and pharmaceutical claims, which I described before. Now, the problem with this data set is that the feature space is enormous. There are tons and tons, on the order of tens of thousands of billing codes for various procedures and diagnoses. And since we don't know what's relevant to predict specialty, the option of parameters that we have that can derive pattern for are you a cardiologist or not is huge. And another axiom in this space is that the number of labels or known truths kind of has to scale with the number of dimensions that you're going to explore. So if we want to explore tens of thousands of features, the few hundred calls that we have are just not going to suffice. So instead, we have to train, if we want to build a model around this massive space of features, we have to use our bigger, less accurate, more stale registry data. So we built a very complicated model, which I'm not going to describe, against this slightly stale data as our ground source of truth, and got some prediction of whether the different providers in our system are cardiologists or not. But we can do better because we know we benchmark this against the not so perfect data. So this is the piece where I think my team got really creative. And this is not a brand new method, but the way they applied it to this problem really showed that we're able to combine different data sources and apply that intuition and creativity to really get a better result. We have the results from this first model, and we have this data that we think we believe in more, but it's small. Now, what if we took the results of the first data, the tens of thousands of dimensions, turned it into 1 or 2 dimensions, and fed that into a much more simple model against the higher quality benchmarking data to get an improvement over the predictions that we have? And that's exactly what we did. And as a result of that, we were able to get an improvement on about 8 to 9% of providers in our universe. Now, the last layer on top of this is that the numbers are just not the end of the story, right? Before we put this into our product, we have to think about what it actually means. And for this, we apply a layer of medical insight, and we work really closely with a lot of the physicians that work at Grand Rounds. For example, if you're tagged with 2 specialties, one more general and one more specific, can you treat a general patient? In some cases, yes, and in some cases, no. And it really depends on what that combination of 2 specialties is. So before we just kind of throw this into our product and say, you know, you are a cardiologist and you are an electrophysiologist, we have to think about what the impact of the patient is. Can that electrophysiologist treat a patient who just has generic hypertension? Probably not. And so we have to apply this kind of insightful layer on top of the numbers before we ship. All right, so I'm going to stop rambling on with that, but I would like to close with the fact that my team is looking for data artists, and I hope you find us at our career page on grandrounds.com.
Thank you so much, Jayadita. I'm Serena. I work as a software engineer at Grand Rounds. I wanted to open up the table for questions for Jayadita. I wanted to start by asking you, you started off as a IC at Grand Rounds, and now you're a manager, you're the director of data science. What was that like moving, and what were some of the biggest challenges that you faced moving from an IC to being a manager of an entire team?
So first of all, it was really fun for me. I really enjoy mentoring and teaching. That's what I miss from my academic life. And so it was a great way to connect back to that and kind of support the team in a different way. The biggest learnings and the biggest challenges, though, I think in that transition is that you don't kind of get managerial skills for free. It's not something that's just inborn. It's something you have to really work at. You have to kind of have the right mentors and kind of gain from their experience and continuously try to learn this brand new skill set that's very different from an IC skill set, so that you're doing the best for your team.
Cool, thanks. Does anybody else have any questions? Yeah.
Hi, my name's Tushar. Question, the registries that you're using for public, which ones are they? I mean,
you want all the dirty secrets.
I'm guessing you're using NPIs and billing addresses, but what do you do with institutions where there's like an ACO or there's multiple physicians practicing in one billing location?
So we're lucky. So I think there's 2 questions in there. Like, what are the kind of the nature of public data sets that are out there? And then kind of, are they at the institution level or are they at a provider level, and maybe both, and how you resolve those differences. So there's certain public databases like NPPBS that kind of everyone has access to, as one example of the types of data sets we use. And kind of what is behind there is the fact that multiple of these things exist, both publicly and commercially. And that's kind of the art of this, how we combine all of that together. Your second question is whether the data exists at a provider level or an institution level, and the answer is actually both. And in that particular data set I described, it does have the data at a provider level as well. And so we're able to leverage that just directly in our models.
Cool. I think we have time for one more question.
Yeah. Very similar answer you're going to get as well. We have multiple different sources for our claims data, both commercial and public. By the time, all of the commercial data that comes to us is completely de-identified by the time it gets to us. And regardless of whether the source is our own customers or public or commercial, all of the data is identified before it hits the data science team.
Cool. Thank you so much. Next, I want to welcome up Olivia from Synthago. She works as a data scientist. How many of you guys have been to one of the Women in Tech events that we've had at Grand Rounds? Wow, that's actually quite a few people who aren't from our company. Yeah, we're really excited to have this data edition at Grand Rounds. And well, here we go.
Thank you. All right. Imagine that you're at work and one of your colleagues approaches you with a problem that they want your help on. Your company is considering purchasing a new piece of technology, and you already have a current older version of the technology. And your colleague wants help making a data-driven decision. Your colleague wants help making a data-driven decision as to whether or not they should purchase this new technology. On the one hand, it will increase your production throughput because you'll have two running in parallel. But on the other hand, there's some risk in case it doesn't perform as well as your current technology does. So while we're getting this slide up, maybe if we can all ponder that. Cool. So hi, I'm Olivia. I work as a data scientist at Synthico, and we're a biotech startup based in the Peninsula. And we offer genome engineering solutions for folks in academia and industry. And we're tackling this problem through a mix of chemistry, hardware and systems engineering, software engineering, and as a component of software engineering, data science and engineering. Now in the cartoon on the left, you can see our flagship product, synthetic guide RNA, that's directing a CRISPR-Cas9 enzyme to cut at a specific sequence on DNA. So if you reflect back to the question that thank you. So the data at Synthico ranges from predictive, where we model our data, we ask future-facing questions of what do we think is going to happen. But we also work on data at the other end of the spectrum, where we ask the question, what do we think happened for this particular experiment or smaller batch of data? And while there's obviously a lot of value and power that we can glean from these predictive questions, I argue that there's also a lot of insight that we can gather from that experimental smaller batch data. And that's the data that I'm going to be focusing on today in this presentation. So if you reflect back to the question I asked about vetting a new instrument for use at your company, this is actually a situation I found myself in not too long ago at Synthico, where a colleague approached me with a question about purchasing a new liquid handling robot. At Synthico, we use liquid handling robots primarily as part of our post-processing, where we try to remove impurities of interest from our product. So my colleague had already generated data, and the way he had generated it was to take a sample batch of pooled material. He aliquoted out 120 samples, halved the batch, that 60 samples went to this new instrument we were thinking about buying, and the other half went to our current instrument. And then he measured 4 different impurities that are really critical to our products for each of those samples. And at the end of the day, using this data, he wanted to ask the question, should we purchase this new instrument or not? Now, translating that business ask into sort of statistical jargon, we'll set our research hypothesis as the new instrument performs at least as well or better than our current one. And so we can greenlight it for use in production and double our production capacity. So we'll put the burden of proof on rejecting that null hypothesis and minimize our type 1 error. So one of the nice things we can do with smaller data is we have the luxury of visualizing it. And I love visualizing data because you minimize your risk of missing something that you might with, say, a summary statistic. So looking at this data, what I've done here is each one of these dots is an impurity measurement from a given sample, and these have all been normalized against the product spec for that impurity. So at Synthico, we have product specs that are essentially the maximum amount of an impurity that we will allow in a product before we'll even consider shipping it out the door. And so here, the way to read this axis is that 50% means that if we're up in that upper range of the graph, that we've measured half of our allowed maximum threshold. So you can see that for these graphs, we're actually doing pretty well for impurities A and B. Both the current instrument, which you can see in green, and the new one in blue are sitting at 20% below, 20% or below our product spec threshold. With impurity C, you see that the spread of the data increases for the current instrument and that we're outperforming on the new one. So this is a batch of sample that we looked at. Hypothetically, if we saw the similar pattern for the different product batches that we processed, we could reject the null hypothesis and be reasonably confident that we could move forward with the new instrument. But we didn't look at 3 impurities, we looked at 4. And so here you can see that, whoa, this looks concerning, right? This looks different. We've moved from 50% of the product spec to 800%, or 8 times the maximum allowed of impurity that we will have in a sample. And the other interesting thing is that the trend has been reversed. Whereas previously we were seeing this new instrument performing at least as well, sometimes better than the current one, here we're seeing enormous spread and we're way above the allowed threshold. So what's going on in here? So Twyman's law tells us that if a statistic looks interesting or unusual, it's probably wrong. So what are the things that could be going wrong here? So it's possible that for this particular batch, we had a contamination issue, that somehow we truly had 8 times the amount of allowed impurity from that new instrument due to something with a sample batch itself. It's possible, but the other thing that we should look at immediately is our experimental design. And in this case, when we think back to it, we realized that while we ran multiple product batches, we ran no replicates of the same sample. So we're essentially blind to the variability on the current instrument. We're also blind to the variability on the new instrument. The question that we asked was, given this set of data, are we confident on bringing up this new instrument? When the question really should have been, can we expect with reasonable confidence that we can reliably and repeatably expect at least as efficacious performance on this new instrument as the current? And we don't have the data to answer that because we didn't design our experiment to answer that question. So clearly there's an experimental flaw here, but I would argue that's even deeper or more fundamental than that. The order of this experiment was, colleague approaches Olivia with data. Olivia thinks about hypothesis test and decides on a particular method to run, and then analyzes and interprets the result. The first two should have been swapped. We should have designed our experiment first, decided on our hypothesis test, decided on the success criteria up front, then collected the data, and then analyzed the data according to those success criteria that we set up at the onset. And the point I want to make is that I gave a biotech example. This is kind of a sciencey, traditionally a sciencey concept of experimental design. But as many of you already know, we run experiments all the time in all types of different industries and across all levels of technicality in our organization. If we're in marketing, we run A/B testing. For software development, product management, we do the same thing. Mechanical engineering, you run materials properties tests, usability tests. So this isn't a unique biotech concept. And the other thing that's powerful about this, I think, is that you don't need a PhD in statistics. You don't need to be an expert in machine learning to have a shift in sort of the attitude and culture from a data before design perspective to a design before data perspective. And I want to thank Grand Rounds for hosting and all of you for your attention.
Thank you. Does anybody have any questions for Olivia? I just wanted to start off by asking you then, what surprised you most about working in biotech? Seems like it has a lot of unique challenges.
Sure. So I think one of the interesting things about biotech compared with other industries is that experiments can be expensive. So in this case, you'll notice that the size of the data is smaller than certainly, what we associate with big data or even medium data. And biotech is, the experiments are costly to run from a materials perspective. From a startup perspective, I'm sure many of you know there's sort of a push to move fast, break things fast, move quickly. But in biotech, you have to balance that. So I think the first thing that's surprising is the cost of an experiment, and that being a really key thing that you have to think about. And that drives an even greater need, I think, for effective experimental design, because the cost of misdesigning an experiment is high. And I think the second would be sort of balancing the speed with, it's obviously a highly regulated environment, and making sure that you are doing really rigorous science.
Cool. Well, thank you so much, Olivia. Anybody else? Questions? All right. Well, you guys can, yes, Adam.
Yes, we were. So at the end of the day, we all met back, and my recommendation was, okay, let's redesign this, get replicates, and we realized that the new instrument had sort of a configuration issue that we were able to tease out of the data. And after we updated the configuration data or the configuration issue, we got reliable data back and we were able to greenlight it with no issue. So.
Awesome. Next, I want to welcome up Lindsay, and she works at, another round of applause for Olivia. Thank you again for coming all the way to Grand Rounds to speak. I next want to welcome up Lindsay. She works as a data engineer at Grand Rounds and has quite a few fans in the room, and is going to talk about how automation is a huge opportunity.
Great, thanks, Serena. Hey, y'all. How's it going? We're waiting for my slides to come up. Cool. So in the meantime, you know, I guess okay, there we go. All right. Cool. As Serena said, my name is Lindsay. I am a data engineer here at Grand Rounds, and I've been here for almost 2 years now. So how did I get here? Yeah, somebody gets that joke. Thank you. So it turns out that actually before this is my second career as a engineer. I was a musician for a really long time and working in like retail and food service and odd jobs and stuff like that. And then about a little over 5 years ago, I decided to go back to school. And I took my first computer science class kind of on a whim. And my first Hello World program in my first class, it just like blew my mind. I was like, basically it kind of feels like the first time that I learned a song on piano when I was like 9 years old. And I was like, oh yeah, it's like when you're playing chopsticks and you hear that song that you know is in your head and then it comes out of your fingers. It's the same thing with like the Hello World. I pushed the button, my code ran and it said Hello World. And I was like, all right, I'm here. So, and it turns out that there's actually a lot of transferable skills you get in between, you know, creative arts and, you know, scientific things, just like Jay Odita was mentioning earlier. For me, this ends up being sort of like I can see a bigger picture in a lot of things, which is really handy. So for example, like I play bass in some bands and I can understand how my notes are supporting like the guitar and the melody of the singer. And in the same way, I can see how my work as a data engineer actually supports our work for the rest of the company with our data science and data analytics teams. So I also tend to have a knack for organization. You would not know that by walking into my house, but I actually am pretty good at seeing similarities between things and kind of compartmentalizing them, which can be really handy when you're dealing with a lot of messy data. And also I've always liked math, and it turns out that data pipelining is basically just gigantic functions. You're taking something from over here and you're trying to put it over here, and you want that to work the exact same way every single time. And of course, because I work here at Grand Rounds, there's also that whole saving lives thing that we do. I kind of like that too. So before data engineering, Ancient BDE, we just had a lot of people handling our data here, and it was a very slow process. We had these gigantic spreadsheets, and we were doing a lot of manual edits to basically normalize the data and make it look nice so that our data science and analytics people could actually you know, derive their insights. And then we were having manual loads into our database tables. This turns out to be a very expensive operation. You have somebody literally manually going in, like editing spreadsheets and putting them into databases. It takes a really long time. I think one quarter, there was like 240 hours that went into just loading files into databases, which was crazy. So of course, we had to decide to automate that, and that's when our data engineering team was created. Basically, it was, you know, this was created out of a need to like handle our data in a much more automated and streamlined way so that we didn't have to do so much manual work on it, and that meant that we could move a lot faster. So has anybody heard the term ETL? Great, awesome. Okay, and you guys, does anybody want to shout out what that means? Great. So for anyone who's never heard that before, it stands for extract, transform, load. And it's actually a pretty standard way to operate on your data and create a pipeline. So we started building it. And so the E came first, the extraction part. And basically, what that comes down to is that our customers have to deliver us the data, whether that's they're directly sending it to us or whether we have to go retrieve it from them. Somehow it has to get from them to us. And when we do that, my opinion is that this is actually the most, this has to be the most secure part of this whole process. And the fact that like, it's actually crossing thresholds. We can keep our own system pretty secure. They can keep their own system pretty secure. But when it has to cross over those thresholds, you run into a lot of security issues. So we have to be very careful at this point. But we were trying to decide how to automate this part. And there's kind of two different strategies that you can go with on this. You can either make it a time-based retrieval or you can make it inventory-based retrieval, but they kind of end up being sort of a hybrid thing. So with us, we end up saying we have a server that we basically just run a job every so often. It's a cron job, and it goes and it checks for new data at one of our data sources. And if there's anything new, it retrieves it for us. So actually, it's a pretty simple process at that point. So then the next thing you have to do is transform the data or transfigure it. And so, oh, and I should mention that the first part, these first two parts of our pipeline are actually built in Ruby on Rails, which is, from what I understand, is actually not super standard. A lot of people tend to do this in Python as well. So we, decided, okay, well, what's the next thing we have to do? We have to transform the data that we have retrieved. So as the saying goes that everybody has heard in this room, data is dirty. It's got lots of different problems with it. It can be missing, it can be incomplete, erroneous. It can be all sorts of different formats, which is actually something we have to deal with. We have lots of different vendors that are sending us this data. And so we had to say, well, how can we automate this? We ended up coming up with two different steps. The first thing we have to do is privatize this. I forgot to mention the specific data pipeline that I work on for the most part is actually for our insurance claims data. Somebody had a question to GeoData earlier about how we make sure that, oh yeah, it was you, how we make sure that our data is de-identified and secure by the time it gets to our data science and analytics teams. That's what I work on. So this is your answer. So the first thing we have to do is privatize it. That means we have to stay HIPAA compliant, and we also have to completely de-identify it. There is a challenge in this though, in that we have to make sure that even though we've de-identified it, we want to make sure to be able to follow and know that like we're looking at the same person's claims without knowing who that person is. And then after that, we have to normalize the data. So there's a few different things that go into this, but basically we, it's simple things like making sure the decimals are all in the right place, that your column names are all matching, trying to decide exactly which data you want to keep when you get into this step. And then after that, oh yeah, I'm going to give you an example here. Okay, so so here I've made two basically like cute little tables of like 3 claims each, and obviously these files that we get are actually like millions of lines long, and they have like a lot more columns than this. But here's a small example of what this could look like. So our first vendor has sent us the format that looks like this, and our second vendor sends us data that's raw that looks like this. And so we need to decide first like how we're going to privatize it. So obviously we don't want any identifying information in there, so we're going to go ahead and take out the first name and last names, and this is basically going to come from a configuration file that we have for each one of our vendors. We say, oh, in this vendor, the first name is this thing, and in this number, if in the last name is this one, and then here's a handful of other stuff that we want to take out. So we're going to go ahead and remove Ophelia Payne and Cerebellum and all of those, and we're going to turn those into a patient ID. The hashing function is just my brain in this one, but we have like a hashing function that we use. And then now we can see like, okay, well, this is obviously the same person, but I don't know anything about her. So, or them at this point. So there is a human there, but we don't know who they are. So then after that, now we have to normalize the data. So I mentioned earlier, one of the things is, of course, just changing your column names. So we want to actually change those into standardized names that we have decided on. And for us, this is just the most readable format. And then it looks like, so for our first vendor, their procedure dates are actually going to be in a reverse order from what we want. We prefer year, month, day, which is the best format for dates. There's some feelings on that, I know. And then for our money columns, we actually decide that we want to keep decimals in there. So we're going to go ahead and change those dates around, and we're going to put some decimals in this one. And then we actually have like a uniform format now for all of these things. So the next thing that we have to do is the L part, which is loading. We actually, when we got to automating this step of the process, we actually ended up using Airflow, and we have somebody, Belinda, I think, is speaking from Airbnb. Hey, Airflow has been really awesome. I've been learning a lot about it, and it's great. So we use it basically to help automate the loading into databases that we have. So I mentioned earlier, we used to be operating on like gigantic spreadsheets, but it turns out that databases are way easier to use than spreadsheets for lots of reasons. I'm sure most of you guys know about all that, but you've got multiple user access and like you can store a lot more stuff in a database than you can in a spreadsheet. So, and then also you can, of course, aggregate it across many formats very easily just with, some SQL, basically. So at this point, we have our two vendors, and it turns out we can actually just throw those into the same table. And now we can start looking at this data and see what kind of insights we can find about that doctor who has seen all these different patients. We can look at different, all the different things like how much people are spending on their healthcare. And so, but yeah, the main part about this is that we do get to automate this whole system. So we have all sorts of benefits that we get out of that. We get faster delivery. We get fewer human errors from, we don't have to worry about somebody fat fingering a column name. And, that means that we can process a lot more data in a shorter time, which gives us the opportunity, especially here at Grand Rounds, to save more lives, because now we can find out more information about people's healthcare data, and we can then derive insights, we can drive better healthcare, and we end up saving a lot more lives. So that's what I do. Thanks, everybody, for coming.
Thanks so much, Lindsay. I had a question about how we go about testing, I guess, the transformations that we're doing on data. You talked about how there's fewer human errors, but I'm sure there's still errors in our transforms, or maybe even how we're getting data from vendors. How do we go about testing, and what's some of the maybe more common errors that we encounter?
So basically the way that we test things is we build sample files and then we run them through our pipeline, and the sample files look like raw data that we have basically made up. So you're going to see SpongeBob SquarePants and like Cersei Lannister and whatever in there. But basically then we have a set of unit tests that we go through to make sure that each one of our transformations is working correctly. Like, if we see this information with this spec file, that's going to move the decimals, and if this one, it's not going to. And then we also have a series of integration tests that we run as well. So that way we make sure that if a file starts out looking like this, it looks like this on the other end after it gets all the way through the pipeline. So.
Cool. Does anybody else have any questions for Lindsay?
So are you able to track, for example, the physician across different providers? Different insurance carriers, like Dr. A. Smith, because you've de-identified him. But suppose you got it from insurance carrier A and insurance carrier B.
Oh, we still keep the NPI information.
You still keep the NPI?
Yeah, so we're de-identifying the patients because we want to make sure that like your healthcare information is as protected as it can be. We don't want to know who you are. We just want to know about like how this physician's doing, for example. So yeah, we can see like, how many times you've seen that doctor, but we don't know who you are.
And when you're checking for new data, like how are you basically checking that I have new information related to this doctor versus it's just old information that's going to be duplicated when it gets loaded in? Like, for example, like you have Dr. A, he did procedure B, and we have this information, but now we have Dr. A again, but he's in procedure B and C. And how do you only want to get the new information and not the old information?
We actually operate on like just gigantic files. So we do like a file-based retrieval versus like a claim-based retrieval. And any of those kind of insights are actually done by like our data science team.
And that doesn't slow down the system at all?
No, that's just like every time we get a file from somebody, which has, like all of the recent insurance claims that they've processed through their billing system, then that's what we just send into our system. And then of course there's a bunch of like reduction and stuff that happens and all that stuff. So does that answer your question?
Yeah.
Great. Okay, cool. Anybody else? Yes. Oh, that's a fun one. Oh, so the question is, how do you catch when a vendor changes their file format? So we have a very robust error handling system, and it gets noisy is what happens. So for example, sometimes they'll send us the wrong date format in a column. They told us it was going to be one thing. They'll send us a data dictionary, and then we'll build our spec based on that. And then it'll be like, oh, we tried to process this file, and there's like the entire thing errored on every single line. And so, yeah, that is actually a common problem, which we get to figure out, well, what went wrong? And it turns out that, oh, it's because they told us it was going to be this format. It's actually this one. So we do have to do some manual audits. Yeah, when there's like errors like that, but we've also built up the system to be pretty robust so that we don't have to actually like open up a gigantic file most of the time. So that way we can actually just say like, okay, what exactly does this cell look like on this one row? So that way we can see, why is that throwing an error? Oh, it's because like this is actually a future date. Somebody, typed in the wrong date or something. So we have a bunch of like basically checks like that so that way we can catch them. So yeah. Cool. Thanks, everybody.
Yeah, thank you, Lindsay. I now want to welcome up Belinda, who's a data scientist at Airbnb. I now want to welcome up Liz, who actually came and spoke before at one of our events, and we loved her so much that we asked her to come back.
Aw.
And she's a CTO of Enki.
Hey. I'm going to use my phone. And my slides will appear momentarily. Hey, everyone. I'm Liz. Nice to meet you. Those are not them, but cool slides nonetheless. Very interesting work. Do a little dance. Yeah, I'll tell some fun facts about myself. So I'm Liz. You might recognize me from Hackbright Academy or Galvanize or Tradecraft. I helped start Hackbright, and I helped get Galvanize's web development program off the ground. I also helped them a lot with their data science program. So that's kind of why I know about data and why I'm here. We're so close. I can see them. They're right there. So yeah. I originally gave this talk at Lesbians Who Tech. It was pretty cool. People liked it. So I'm here doing it again. So this is my talk title, Supergiant, and I'll give you a second to read it. Yeah, so using curating machine training data to counteract bias in machine learning. So, oh no, it's not working. It's fine. I'll use the thing. And that's why we have a plan B. Always have a plan B. All right. So this is the main real thesis of my talk, is machine learning algorithms are a bit like children, and you have to teach them right from wrong. That doesn't sound super technical, right? So like, what do I mean? I already went over who I am. I'm Liz, the developer, and yes, I still get asked if I'm a developer. Let's see, I can't go down on this? No, I can, yes. These are all those startups I just talked about. Currently, I'm the CTO of Enki. What we do is we make educational products for developers. I also wrote the fraud prevention system that protects your debit card if you have these banks. So, probably I do. And yeah, so I'm a teacher, kind of as I mentioned. I'm also CTO right now, and I'm a mom always. So I know a little bit about learning and a little bit about data. As an aside, wanted to just point out, we are about to launch a chatbot that's going to help you be a better technical mentor. I'd love it if you checked it out, bit.ly/EnkiBot, ENKIBOT. Yeah. I'll just give you a second to do that. Thank you, everyone. Cool. I also tweeted it. So this is a real technical thesis of what I was really talking about. It's another giant paragraph. Well, if you want to read it, the main thing is you should use an inverse reinforcement step. If you are building models, certain models for certain data sets, for certain products, to train a bias into your models, or you're going to get real weird data, and I'll explain what that means. So what is machine learning? A lot of you know what machine learning is. Those that don't, I've attached a lot of beginner-friendly slides, so you can kind of dive in if you'd like. But what I'm talking about for this talk is artificial neural networks. That's kind of the scope. It's kind of the idea that data has features and that we can kind of use small, less computational resource to analyze small parts of those features in conjunction to kind of make a pathway to something that's correct. That's basically kind of what it's like. I've thought a lot about learning. I've thought a lot about what learning is and what's effective for my students, for my kid, kinds of things. Apprenticeship learning is a topic that you're probably pretty familiar with. It's just the idea that with an artificial neural network, such as a neural network that's going to play chess, for instance, and it will observe its environment, the configuration of the board. It will make some action, right? And then it will observe its environment and say, okay, am I closer to, my goal? Now, the way that we train neural networks is by giving them training data, right? Apprenticeship learning is where you give a neural network training data that is good and training data that is bad, like not a good example. These are called expert trajectories. And what they allow you to do, and I've linked the papers down here, what they allow you to do is kind of give your model a place to start. So if you're trying to build a model that wants to classify something or take a series of actions or decide how to allocate resources, using apprenticeship learning is a pretty cool method. It's very similar to stuff that you have actually experienced as a person when you were learning, right? What we do when we teach people is we show them examples, good and bad, right and wrong, and we look at their examples and we correct them. You don't, when you're teaching a machine, look at the examples and correct them, but you do show them, how to classify things by giving them a series of examples. This is like this is reinforcement learning. Apprenticeship learning is called inverse reinforcement learning because what we do is give mostly expert trajectories first. Then from there, let it explore with a reward function. So I want to get into what I mean by bias when I'm talking about like removing bias in your data. I'm talking about the actual bias in your data, not the part of machine learning that is called a bias. You need that for a machine learning algorithm to work. That's just how they work. But what I mean is prejudice in favor of or against one thing. Because the thing is, your data has a bias in it. If what you're trying to do is classify things like tweets, for instance, like hate speech or spam, your data is going to have a bias in it. And this, I'm not sure if you've seen this graph before, but this, there's a machine learning thing that we've created, linked up here, that predicts how you might engage with content on Twitter. And what we found is that the more moral, emotional words there are in a tweet, the more likely you are to retweet it, right? And so to elevate reach. I'm sure you've noticed this thing on Twitter recently. There's like, in case you missed it, it's on there. A lot of social networks are doing this now. And this presents a classic problem in using a machine learning algorithm to pick what goes in that, called the multi-armed bandit problem, which is where you're trying to like efficiently figure out like what should go in there, what's the best set of content, right? So usually, I mean, you could probably take a guess, but this is liberal Twitter and this is conservative Twitter. And this is how often they retweet each other. Not a whole lot is the answer. So, so if we're predicting how you might engage with content and we're optimizing for engagement of content, right? You're gonna retweet your in-group and you're not gonna retweet your out-group, right? But the thing is, if you're using a machine learning network and you're not like, you're not just picking like, you know, what are my friends we treating? You're just allowing kind of any feature to be selected. This is what we're talking about when we talk about inverse reinforcement learning is we have to find the reward function. We don't know it really in advance, right? And so these expert trajectories have made sort of a value statement, an assertion. This is the winning state, this is what winning looks like, right? So if, you know, we allow like children to kind of, we don't tell them what the reward mechanisms are, right? We don't say this is what's good and this is what's bad. So they figure it out. And so you can kind of see this up there. There is the candy, right? She is not supposed to be doing this. She is exploring the boundaries of which actions will get her to the reward. There's this paper called Concrete Problems in AI Safety. It's really awesome, written by a lot of different people across the industry. If you haven't read it, you should definitely read it. It's kind of what this talk is really about. The idea is that not all metrics are good reward metrics. You can't just allow your autonomous agent to explore and decide that anything is a reward function. You have to use expert trajectories if you're gonna allow reward function exploration, and if you're gonna allow, if you're gonna allow a machine learning algorithm that definitely has the intelligence of a toddler to elevate content that millions of people see, like we're kind of letting a toddler control the national discourse. Maybe not a great idea. I think we've seen that. I don't feel like I have to establish it with a paper or anything. So, but yeah, this is a great site to check out. This site is basically a graveyard of machine learning algorithms gone awry a little bit, as charted here. So the thing to keep in mind, and this is less applicable to biotech, but when you are doing content suggestion, you have to understand that it is training your users. When you say something and a bunch of people retweet your stuff or validate it in some way, you're giving a user a reward function. Their neural network is receiving a reward of attention from their peers and their friends. And so when you write these algorithms, if you don't add a step that strongly disincentivizes things like hate speech or fake news, these are features that we can find. MSMBC is different than MSNBC. These are like, features that can be looked for and searched for and taught to content suggestion algorithms as strongly negatively weighted things. The same with hate speech. The paper that's linked here, this paper, super awesome, talks about how to do that. There's another paper here. Sorry, my slides are like a maze. You can use this tool to detect overly homogeneous training data. The idea is that lots of people use this thing called cross-validation to see if their models are accurately predicting whether or not, something is something else or something is a good, they use cross-validation to, validate that a model is classifying things correctly, right? But if you're classifying something as a high, or choosing something as a high probability of, getting engaged with, thus making people stay on your site, if you have extremely homogeneous training data in one set, you're going to basically train an algorithm to tell you, to elevate things that are not really okay to elevate, right? So the other problem that you run into is that the signals of the world don't average to the truth, right? If you kind of let your machine learning algorithms decide their own reward functions and run rampant, I'm sure you remember the Twitter bot that like turned into like a hate bot really, really fast, right? There's a lot of adversarial data out there. So if you're creating a content suggestion algorithm, you have to be aware. It's just like Google's search algorithm. The whole field of SEO is basically adversarial data, right? It's meant to make an algorithm make a decision that is not actually related to what the algorithm intended, right? At DEF CON, adversarial data has been shown to be able to change this panda image to be a gibbon. But, that doesn't sound super scary, right? But like, also we have a lot of image classification algorithms that are used in a lot of different areas of life. And so like consequences are kind of a big deal. If you only take your training data and you're going to classify this as a pistol, right? You need to look at that training data and find out what are the demographics of the people holding the handle of the pistol. Because otherwise you're going to train a machine learning or an artificial neural network to classify guns wrong. I mean, I'm not sure if anybody's working on this, but there's smaller and less scary examples of this all over the place. The other thing to keep in mind, though, is that, this is what they thought rock music was, right? Don't create a censorship algorithm that like stays away from all the naughty words. Like that's not what we want to do. So you as a person, you have to like raise your kids, right? Like your machine learning algorithms. You have to pick some data, put strong negative weights against things that you don't want elevated, and you have to pick, expert trajectories for like things that you do want elevated, things that are legitimate sources, and together we can maybe fix this whole InfoWar problem. Like it's you guys, this is all of us here in this room and a number of other people that need to be convinced that we need to take these kinds of steps. So yeah, that's my talk.
Thank you so much, Liz. That was really interesting. I had a question going back to one of your slides where you're talking about detecting homogeneous data. It seems like a lot of data collections would just like inherently be homogeneous to at least a certain degree. So what does it mean to be like a homogeneous data set, and how do you go about detecting it? I don't know if you can like summarize it or
yeah. Well, so the
that.
link in the link on the slide will give you this example. Kodak used to only test their films with these models called Shirleys, right? And Shirleys are usually beautiful redheads who are white, extremely, extremely white. And that was their test model for, is the film batch okay? And do the colors work out right? Which like caused a lot of problems in the 50s through like the 70s, I think, where black families would take, or brown people would take pictures of their families and they would just be super dark or like really, really washed out because they just didn't test the film on people who were darker than like, extremely, extremely pale people. And so they didn't see the range of browns change. And that's overly homogeneous data that they couldn't use to make a good decision. Overly homogeneous training data is all over the place when you need one person to look at it to validate it. So mainly this is the argument of like more diverse teams make better software, or products. And so, there's a lot of examples in that thing, but that's kind of the idea there.
Cool, thanks. Yeah. Does anybody have any questions for Liz? There is, yes. You want the microphone? Okay.
Shout it.
Could you repeat about the picture?
Okay, so this slide talks about like, we're classifying, this is a panda, and then we change it, and then now it's a gibbon, right? So, that's not right? So this image classifier is 86% sure that it's a pistol, right? So let's say that we went and we trained this on like all the movies, you know, that would produce a very different data set than if we trained it on a CCTV, you know, that's in color and is well defined enough set of, you know, like security camera images, or, you know, that's what I'm kind of talking about. I'm not super sure what your question was. The what? Oh yeah, yeah. So that's the other thing is, you know, we're training a lot of computer vision stuff right now to like recognize things like weapons, right? Boston Dynamics has a bunch of papers about this. And I think they've been talking about, you know, you can't use training data from films because the person holding the pistol will affect whether or not the pistol is accurately classified as a pistol, which I feel like we hear that in the news all the time, you know, like these forces that act on machine learning algorithms are the same forces that are acting on people. It's just seeing things over and over and over again. So if your machine learning algorithm is only exposed to like the FBI criminal database, what are the demographics of that database? You know, you're gonna see that same bias in your data, right? So that's what I mean. Yeah.
Speaking of algorithmic bias, how do you feel about things like the Algorithmic Justice League or the book Weapons of Math Destruction?
I have not read those books. They sound wonderful.
Well, one is an organization,
Great.
the other one is a book.
Well, sorry, yeah, that first organization seems awesome, and I want to be in it. But yeah, no, that sounds really awesome. The book that inspired me, it's in here somewhere. Is it this? It's this one. Noam Chomsky. Yeah, manufacturing content. Read that. It's really good. It will help you understand what's going on in the world. Always.
Cool. Thank you. Oh, well, we have one more question.
It's everybody's responsibility, but let's be real, who's gonna do it? It's us, right? I mean, like, it's people who are going on their, you know, weeknights to events where we're gonna talk about diversity and we're gonna talk about women in tech, and we're, you know, we're the ones who have demonstrated that we have the energy and the time. Maybe you don't have all the energy and the time, but you all have the inclination. So I just kind of wanted to say to all of you, please read this book and help me out, because no one else is going to do it unless you nag them to death. So like, it's also a little bit up to us to nag everyone to death about it. So, you know, let's nag everyone to death and also like do it ourselves, since we're data nerds and perfectly capable. But yeah.
Thank you so much, Liz. I wanted to thank Liz, Olivia, Belinda for all coming here today and like giving your talks. You know, it's raining outside and all of you guys came and we really appreciate it. If you work at Grand Rounds, can you raise your hand? All of these people are from different departments and engineering and product and accounts, I think. Yes. And we'd all love to talk to you about Grand Rounds and learn more about you. I think Liz and Belinda and maybe Olivia will stay around if you want to ask them questions. Thank you so much for coming tonight. We really appreciate it. And yeah, there's more food, more drink. Enjoy.